Problem A2. For this problem, graphical answers should be drawn on the answer sheets, graphs provided. Supporting work is to be written on blank answer sheets. Incorrect graphs without supporting work will receive no partial credit. The current I as a function of voltage V for a certain electrical device is next one, where Q is the magnitude of the charge on an electron, QB is Boltzmann's constant, and T is the absolute temperature. I0 and V0 are non-zero positive constants. Throughout this problem, assume low temperature values KBT much less than QV0. Question A. On the answer sheets, sketch a graph of the current versus voltage for low temperature values KBT much less than QV0, clearly indicating any asymptotic behavior. Solution for problem A2. Question A. The current is simply proportional to this expression, which is shifted exponential. Then I always has the same sign as V and vanishes when V vanishes. The current grows quickly for high V and approaches zero for low V. This answer is acceptable, but we can use the condition that KBT much less than QV0 to simplify the graph. For negative V, we have I over I0 approximately equal negative E in power this one, which is extremely small. For positive V, we have I over I0 approximately equal this expression, which is extremely small when V less than V0 and extremely large when V greater than V0. Then we have this answer. Accounting for finite temperature, which is not necessary for full credit, simply rounds the corners in all of the graph, and the final graph should look like this. This is answer for question A, and this was the solution for this question. Shown is a schematic for the device. Positive voltage means that the electric potential of the left hand side of the device is higher than the right hand side. For this device, I0 equal 25 microampere and voltage and V0 equal 1 volt. Below is a circuit made up of these elements. The voltage supplied the circuit is sinusoidal. VAB equal VA minus VB equal VS sine omega t, and is also shown on the answer sheet. The resistance is R equal 5 ohm and the S equal 5 volts. Question B. Sketch the potential difference VCD equal VC minus VD as a function of time on the answer sheet. For your convenience, VAB is shown in light gray. Assume that VAB has been running for a long time. So that's the answer sheet. Solution for question B. When absolute value VAB less than 2V0, no current flows. When absolute value VAB greater than 2V0, current begins to flow which with each diode subtracting a potential difference of V0. Note that the current flows in the same direction for both positive and negative VAB. This device is a rectifier. Now a capacitor is connected to the circuit as shown below. The capacitance is 50 microfarad. Question C. Sketch the new potential difference VCD equal VC minus VD as a function of time on the answer sheet. For your convenience, VAB is shown in light gray. Assume that VAB has been running for a long time. So that's the answer sheet. Solution for question C. Let the voltage on the capacitor be Vs whenever absolute value for VAB greater or equal to Vs plus 2V0. Current flows through the diodes, charging the capacitor up to voltage absolute value VAB minus 2VA0. Whenever absolute value for AB greater or equal to Vs plus 2V0, no current flows through the diodes, and the capacitor and the resistor simply discharge as an RC circuit with time constant equal to 250 milliseconds. Since RC is much longer than the time scale on the answer sheet, the discharge is approximately linear, with dVs over dt equal to 1 volt over 83.3 milliseconds. Thus, the capacitor charges completely to 3.0 volt every cycle, then discharges approximately linearly by about a half volt during the remainder of the cycle. On the graph we show charging as red and discharging as blue. So that was a solution for question C, and that was problem A2.